Hey everyone, disembodied voice of your professor here. I'm in the middle of the storm. It seems to be raging outside, if you can hear it. And what I wanted to do today was to finish up the very last of what we had to do with independent samples t-tests, and then spend some time differentiating between the three kinds of t-tests that you're going to be asked about when it comes to Friday's exam, and another example for each one of them about how to do them. So here it is that we go. I'm going to go ahead and start at the beginning of the example that I was running through on Friday. If you all remember, it was about Hogwarts, and we had the comparison between Hufflepuff and Ravenclaw in terms of how many people each one of these populations snog on over the course of an academic year. This is necessarily an independent samples t-test because different people are in different groups. Ravenclaws are different people than Hufflepuffs. So here's the null and alternative hypothesis. The null hypothesis is that both of those populations are in fact the same on average when it comes to snogging partners. The alternative is that they are not the same. And the upshot of that is that if they are the same, then the mu of one minus the mu of the other equals 0. That's the null hypothesis. So the typical or average result we should get when we take a sample of each is that the difference between the samples will be 0. On the other hand, if the two populations are different, then typically when we take a sample from each and subtract them from each other, we should get something other than 0. Okay? So we don't know anything about the populations. We are just going to have our raw data and make an average out of each group. That average of the first group, Hufflepuffs, is going to be X bar sub 1. The average of the second group, the second sample, is going to be of the Ravenclaws, that's X bar sub 2. We are going to analyze whether the difference between the two means is big enough to be statistically significant. So therefore, the statistic for analysis is the entire phrase X bar sub 1 minus X bar sub 2. All right. Every time we do a hypothesis test, we also need a standard error. This one is a little complicated. It is this formula here at the bottom. It involves taking the sample size of the first group, N sub 1, the sample size of the second group, N sub 2, and the standard deviations from each sample. That's S sub 1 and S sub 2. In this formula, you'll notice that before we do anything else to the standard deviations, we are squaring them. That actually gets us back to, if you remember, variance. It's not really important now, but we are going to get back to variance in a chapter or two. Put all of those numbers into this complicated formula, and it spits out the standard error. That which used to be S sub X bar or S sub D bar, now it's S sub X bar sub 1 minus X bar sub 2. All right, so here we are. We're going to take an alpha of 0.05, as usual. Here is all the information about Hufflepuff. I took a sample of them. I got an average of 5.14. There were 14 Hufflepuffs, and the standard deviation among those 14 people was a 1.66. For the Ravenclaws, they averaged slightly fewer snogging partners at 3.75. There were 12 of them, and the standard deviation among Ravenclaws, those 12 Ravenclaws, was 1.71. Now, I said that was slightly less, but I don't know that for sure because we haven't done the test to see if 3.75 and 5.14 are statistically significantly different. Here's our statistic for analysis, though. Hufflepuff mean minus Ravenclaw mean is 1.39. 1.39 snogging partners is what separates these two means for these two samples. Is it statistically significant? We don't know yet. When we finally figure out our test ratio, we're going to have to compare it to a critical value as always. But here's the new part that we hadn't covered in class yet. When you are getting the degrees of freedom for an independent samples t-test, what you're going to do is add the degrees of freedom from the first group to the degrees of freedom from the second group. That's number of people in the first group minus 1 plus number of people in the second group minus 1. Or, if you want to make it easy, add everybody in both groups together, and subtract 2. So in this case, 14 Hufflepuffs plus 12 Ravenclaws is 26, minus 2 is 24. So degrees of freedom in this example is 24 degrees of freedom. If you look that up on the T table, if you go down to the 24 degrees of freedom, you go over to an alpha of 0.05, you get a critical value, a T crit of 2.06. So our statistic for analysis, x bar sub 1 minus x bar sub 2, has to be a little bit over 2 standard errors away from 0 in order to be significant. So all we have left to do is to figure out how many standard errors away from 0 1.39 snogging partners actually is. All right, here is working out the standard error. Again, I'm never going to make you do this on a test. I might make you do it on an in-class assignment, depends on time. But this is how all the math would shake down. Okay, it's this very simple arithmetic. There's just a lot of it. By the time it's all done, we realize that the standard error is 0.65. That's taking into account how diverse both samples were, how many people were in each sample. We get an S sub x bar sub 1 minus x bar sub 2 of 0.65. All right. So how many standard errors is 1.39? Well, 1.39 minus the middle of the distribution, which is 0, as it always is. If the null is true, the middle of this distribution is 0, divided by the standard error, and you get a 2.14. We needed 2.06. So this would be a significant test. Not by a lot, but it's significant. Since our test ratio is bigger than, in absolute terms, the critical value, the difference observed between the mean snogging partners of Hufflepuff and Ravenclaw samples was less than 5% likely to have happened if the two populations were actually the same. Okay, and so that means that it is statistically significant. Got it? That's independent samples t-tests. Now, what I'm going to do for the rest of this talk is to try to help you differentiate whether you are dealing with a single sample, a paired sample, or an independent sample based on the setup. So I'm going to ask basically the same research question in 3 different ways on the next few slides. CNU student body has a mu GPA of 2.85. I made that up. I don't know if that's true. You take a sample of 37 members of the Greek community to see if their GPA is statistically significantly different. So this is testing whether Greeks have a different GPA from the mu overall student population. The Greeks got an average of 3.13 with a standard deviation of 0.84. What statistical test would you use? Okay. This is where we use the hypothesis test flowchart. The first question is, do you know sigma? Well, I didn't give you sigma. Okay, all I gave you was the standard deviation in the sample. So that would be a no. How many groups did we have? I only measured one group. I only measured the Greeks. Okay, so I do have a population that I can compare that to, but I only measured one group. Did I measure them once or did I measure them twice? I just measured them once. I measured 37 people, got their GPA. And so what we're going to be dealing with here is the single sample t-test. That's all the information. In this box right here. Sorry, tech glitch. All right. Then I get a critical value. I get a test ratio. I figure out which one is bigger and then make my decision, reject or fail to reject. Okay. If I had given you sigma, that would be the left-hand box over here. We would use a Z table for a Z score. We didn't. We're using a T table with a T score over here. All right. Next one, same basic research question, different setup. I sampled 35 CNU students, regular, non-Greek. Hold on a moment. Let me make sure I don't run into another tech glitch. There we go. All set. All right, I sampled 35 CNU students, and I'm recording their GPA in the semester before they rush when they were members of the regular student population. They got an average of 2.85. Then I measured those same students again after they rushed. The average was 3.13. The standard deviation of the different scores was 0.03. What test would you run to see if there's a statistically significant difference between Greek and non-Greek? Well, if you don't have that down intuitively, let me run it past you again. Did I throw you a sigma? Nope. No sigmas involved. I didn't give you any parameters at all. How many groups did I measure? Just one. I measured one group of people. Okay, that was the same people. Did I measure them once or measure them twice? Well, I measured them twice. I measured them once before and I measured them after. So that's going to be a related samples t-test. I'm going to take everybody's score after they rushed, subtract their score before they rushed, get a set of different scores to analyze. Once again, I'll get a test ratio and I'll get a critical value off of the t-table. Next. I sampled 45 non-Greek CNU students. They got a GPA of 2.85 and their own standard deviation among those 45 of a 0.61. I also sampled 26 Greek students and got a mean of 3.13 with a standard deviation of 0.84. What test would you use to see if these are statistically significant? Well, once again, did I throw you a sigma? Nope, I almost never will. How many groups did I measure? 2. I measured one group of people who were non-Greek, and I measured a completely different group of people who were Greek. So that is an independent samples t-test, and you'll use all the information about independent samples in order to do that one. Okay? That little setup is going to help you here. These are another 3 ways of answering the same question, but I'm going to actually run through the hypothesis test with you to show you all the different parts and how they work. All right, this is true. The psych department is actually considering adding a lab section to this class to get our students better prepared for graduate school, in which our quantitative, believe it or not, is relatively weak compared to other schools. The mu GRE math score for CNU psych students is, and I made this up, 157. We chose 9 students at random and made them take the lab section. So I'm interested in knowing whether people who don't take the course at the lab section end up with a different GRE math score than the people who didn't take the lab section. So here are the results from my 9 students. 164, 165, 155, 156, 168, 163, 163, 160, 155. Okay. The question is, did we significantly improve GRE scores alpha 0.05? Hopefully, I don't have to point this out and you already know that this is a single sample t-test. Big clue, I gave you a mu for the null hypothesis. Second big clue, I took a bunch of people and I measured them, but I only measured them once and there was only one group. So here's what that would look like. The null hypothesis is that the population from which I gathered lab taking students has a mu that's just the same of people who didn't take the lab, which is to say 157. The alternative hypothesis, oh, that should be a not equal sign. Sorry about that. The alternative hypothesis is that the mu doesn't equal 157. Sorry about that typo. I hope it doesn't persist. All right. The first thing you need is the average, the mean of everybody who took the lab section. That is, add everybody's scores up, divide by 9, you get 161. The other thing you'll need is the standard deviation of everybody who took the lab section. That is applying this old formula that I won't go into detail again, but getting a standard deviation by summing up every difference between an individual score and the mean squared, dividing it by n-1, and taking the square root. That gives us a standard deviation among those 9 scores of 4.74341649. Then, in order to get ourselves ready for the hypothesis test, we get the standard error. Taking sample size into account, how much error will there be between samples of 9? This then is the standard deviation divided by the square root of the sample size 9. That gives us a 1.58. So now I can get the test ratio. That is the difference that we observed, 157 minus 161, over the standard error. Okay, and I'm sorry, 161 minus 157, since our average was in fact above the mu, and that gives us a test ratio of 3.97. Our statistic, our X bar, our sample was almost 4 standard errors above the mean. We needed to be 2.306 standard errors above the mean for significance. That is a number that came off the T table, looking down to degrees of freedom equals 8, because there were 9 people in the sample, and over to an alpha of 0.05. So in this case, we have a statistically significant difference between the 9 people in our sample and the population defined as a mu of 157. That's because 3.79 was bigger than 2.306. Next, let's say we didn't have any population information, which is typically true. All we know is that we took a sample of students who took the lab, and it was 161, 160, all through 164. We took another sample of students who didn't take the lab, 157, 156, on through. Is there a statistically significant difference? So now we've taken 2 different groups of people and we're comparing them to each other. The first group had 9 people in it. The second group had 10 people in it. How do we set that up? Well, the null hypothesis is that the mu of the first group is just equal to the mu of the second group, so that when you subtract the 2 population averages, you'll get 0. And typically, then when you take a sample of each and subtract them from each other, you'll get something close to 0. The alternative hypothesis is that they don't equal each other. Therefore, if you subtract one from the other, you'll get a number that's other than 0. Here's information, all of which was pulled from the raw data that was on the last slide. The average, the mean of the first group was of 160. The standard deviation among those 9 people was 3.74165. The mean of the second group was 156. The standard deviation among those 10 people, using just those 10 numbers, was 3.3466. Therefore, the statistic for analysis is x bar sub 1 minus x bar sub 2. It's a difference of 4. We are interested in knowing whether a difference of 4 is statistically significantly different from 0. In order to do that, we'll need the standard error. Again, that's what the formula looks like. I won't solve it here on the slide, but if you put all those numbers in correctly and solved it, you would get a standard error of 1.6256. Now, we put the difference we observed over the noise we expected to get a test ratio. That's T. 4 divided by 1.62, statistic for analysis over the standard error is a 2.46. Ooh, that's close. What do we have to beat in terms of a critical value? Well, the T crit here is a 2.11. 17 degrees of freedom. 10 plus 9 minus 2 gives us 17. So if we went down to 17 degrees of freedom over to an alpha of 0.05, the critical value would be 2.11. We, again, have a significant difference. 2.46 is bigger than 2.11, so it's significant. Okay, last example, last thing. How about we did this, which might be the way to go, actually, be the best research design. We picked 10 students at random and gave them the GRE before they took the lab section, and then gave them the GRE again after they took the lab section. I've listed after in the first column and before in the second column so that we can say if they increased after the lab, then they're going to get a positive score by taking column 1 minus column 2. But this is completely arbitrary. As long as you do the same thing to every pair, and as long as you remember what plus and minus mean, you can get positive or negative values, and it won't make any difference as long as you interpret it correctly. All right, here's how this is done. You would start by taking the after and the before scores and getting a D, a different score for each student. So really, our data set is 213, 453, 2127. That's our actual data set. The null hypothesis is that the mu of those different scores is actually 0. The alternative hypothesis is that the mu of those different scores, the population, is not equal to 0. So if we get a result in our sample that is far enough away from zero will have statistical significance. The average of our different scores here, those 10 scores, is 3. That's called D bar. The standard deviation of those 10 different scores, that's called S sub D, is 1.88. If I just took those 10 scores, those 10 different scores, put them into a standard deviation equation, I would get 1.8856181. The standard error, taking our sample size into account, is 1.8856 divided by the square root of 10. 10 is the sample size. That gives us a standard error of 0.5962847. Therefore, we're almost there. All we need to know is the difference we observed, 3, over the standard error, the amount of noise that we expect, to get a test ratio. And there we have it. 3 divided by 0.5962879 is a 5.03. We are 5 standard errors over 0. That's clearly going to be significant, but what's the critical value, just for fun? 2.264. That is from degrees of freedom equals 9. There are 10 different scores. 10 minus 1 is 9. And that's it. All right, y'all. So have a great day. I hope you're enjoying the weather. It is not even really raining here. I think I mentioned that before. I will see you on Wednesday. We will do our in-class. And again, for those who might have missed the email, the SPSS assignment is extended until Wednesday night at midnight. All right, y'all. Take care.